So if we want to generate a very bright light source, we want to think about how are we creating the light in the first place and how fast does it happen? And so what we're going to look at are rates of these different possible outcomes, our three possibilities: absorption, spontaneous emission, or stimulated emission. So first we'll look at absorption. So the rate at which this is going to happen, so what we're going to consider is what's the rate of change in the number of molecules in state 2. So N2 is what we call the population, or number of molecules in state 2. So we're thinking about how does this change. So we want to think how are molecules moving from state 1 to state 2. So we're going to look at this in terms of this derivative. That's the rate of change of the population with respect to time, right? Since it's a rate. So this is going to be proportional to, well, how many molecules do we have to start with in state 1? A coefficient that we call B12. We call this, so Einstein did lots of stuff. This is one of the things he looked at, is absorption and emission of light. And so this coefficient is named after him. So B12, and this has to do with, fundamentally speaking, the rate, how easy it is for a molecule to go from state 1 to state 2. And so this is directly proportional. This is something that is inherent to different molecules and particular energy levels. All right, so the Einstein coefficient, and then we have how much light do we have? Right, and so this will be, so rho here is the spectral radiation density at the frequency that we need. Essentially, this is how much light do we have? And this is related to similar ideas. The black body equation, rho is that same sort of variable that just it's a variable that tells us about brightness. Okay, so if we interpret this equation, what matters is how many molecules we start with, right? So in state 1, and how bright the light is, and then some coefficient that's related to the fundamental properties of the system. All right. Okay, so that makes sense, right? If we have more molecules in state 1 and the light is brighter, we'll get a faster rate of conversion to state 2. If we dim the light, it'll happen slower. If we have less molecules in state 1 to start with, it'll go slower as well. And eventually, if we have 0 molecules in state 1, no absorption can happen. All right, so that seems pretty obvious. If you have no light, it's also not going to happen. Okay, so that's absorption. For stimulated emission, we get a very similar looking equation. So again, we're going to think about, now it's going to be still the change in the number of molecules in state 2, but overall this is going to be negative, and it'll depend. Now what matters is how many molecules do we have starting in state 2, because they have to start there to cause the emission to happen. And then we have another Einstein coefficient, B21. So this is just the opposite of B12. But these are equal to each other. B12 and B21 are the same. It's the same rate, same fundamental properties. You have the same energy levels, the same difference in energy and everything. So they turn out to be equal to each other, and still the same spectral radiation density here. So the only thing that changes is that we switch, well, first of all, we are losing population from state 2, and it depends on how many molecules we have in state 2 versus how many we have in state 1. All right, and so the last one we'll look at for rates is spontaneous emission. So spontaneous emission doesn't depend on the spectral radiation density, because it'll happen whether or not we have any light present. So the change in dN2 is again going to be negative, and it's going to depend on how many molecules we have in state 2. But now we have a different Einstein coefficient that we call A, that relates to the fundamental properties of how much light gets emitted based on spontaneous emission. So in the next video, we'll combine all these to kind of look at the overall what's happening with our system.